Hello everyone, welcome to IIT and Gate classes. This is your 10th lecture on TOC, and in this lecture I am going to complete the second chapter of TOC, that is finite automata and regular languages. Okay, so in this chapter the 12th topic, or you can say second last topic, is equivalence of regular grammars, regular expression and finite automata. So what exactly I want to say is, see this diagram. Okay, so NFA, DFA both have equivalent power and both are interconvertible. Similarly, NFA with null move also have same power as that of NFA. Please do not think that NFA with null move has more power because null moves are allowed and so on. No, it has been properly proven. Of course, we are not going to prove all these things, but it has been properly proven that NFA with null move, NFA and DFA all have same power. Similarly, regular expression also have same power and regular grammar also have same power. Power in the sense, I have already explained you many times that NFA, DFA, NFA with null move, all these three are known as acceptors. Acceptors means what? These are used to accept the regular languages. Regular expression is used to represent the regular languages, and regular grammar is used to generate the regular languages. Okay, so all these four things are exactly equivalent. Sorry, five. All these five things are exactly equivalent in nature. Okay, so of course their purpose is different, but they all are equivalent. Okay, now next, if you want to prove all these things, of course I'm not going to prove properly, but I will just try to give you small hint about why these are equivalent. So see, first thing, that is finite automata to regular grammars. I have already shown that finite automata can be converted to regular grammar and vice versa. So this is a FA. So how will you convert it into regular grammar? I have already shown you, but let me give you a small idea. Okay, let me give you a small idea. See, let us label this state as S, this state as A, and this state as B. Okay, so according to regular grammar, how we will write? S implies A implies A, or BA or BB, and B implies null. Okay, like this we used to give. If you are not able to remember all these things, then please watch my previous lectures, you will get the idea. So what exactly we are doing? S implies A. Now on A, on capital A, we are having self loop now. So I will say that A, small a capital A, then small b capital A, that is this, and small b capital B. So because we are jumping to capital B state. Now on capital B, since it is a final state, so we are putting null move here. Okay, or you can null production here, or you can say if we have a move like this. Okay, let me give you one move. Say we have a move like say A. Okay, so what we will say here, we will say, okay, here we will say null or A B. Okay, I hope I have made the point clear. If you're not able to follow, please watch my previous lecture. I'm just giving you hint that how FA is converted to regular grammar. Similarly, this regular grammar obviously can be converted to FA also. Okay, so just apply the reverse procedure. And of course, I'm not going into exact details because this is a basic course. In advanced course, I will give you exact idea about how all these things are done and so on. Okay, so please note it down carefully. And I'm just giving you hint that both have same power. Okay, because I have algorithm to convert FA to regular grammar and regular grammar to FA. That's why both have same power. Okay, so please note it down. Okay, let me jump to next slide. FA to regular expression. How will you convert FA to regular expression? This I have not told you till now, so let's do it properly. This is done with the help of Arden theorem. Okay, and there are other methods also, but this is basic course, so I am just giving you idea about Arden theorem only. So what Arden theorem says? Arden theorem says R is equal to Q plus में RP. R is equal to Q plus RP. Here R, Q, P can be anything, that is state, alphabet, and so on. It can be anything, state alphabet combination also. Okay, so let me give you some idea, then you will get it properly. Or okay, let me first explain it. Okay, then I will give you some examples and so on. So R is equal to Q plus RP. So this R and this R are same. So put value of R here. So Q plus RP and then again P. Okay, I hope you have got the point. I am just putting the value of R here. Now Q plus QP plus RP square. I have just opened it. Okay, I have just opened it. RP square. Now again put the value of R here. Q plus QP plus Q plus RP p square. Okay, so q plus qp plus qp square plus rp cube dot 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 dot. Okay, so again I will open up and so on. So just so see it carefully. What will you get? R is equal to qp star. Okay, so q followed by 0p, then 1p, then 2p, then 3p, 4p, 5p, and so on. It will keep on running like this only. So we will get R is equal to qp star. So if we have an equation like this, R is equal to q plus rp, then solution will be R is equal to qp star, that is independent of R. Okay, so the solution of equation is independent of R. This is the main thing. Solution of equation is independent of R. Independent of R. Okay, please try to remember this thing. Now I will explain you how what exactly are R, Q, P, and so on. Okay, so let's take example. You will get it properly. Okay, so let us suppose we have a FA like this, and we want to convert it into regular expression. So how will you convert it? I will apply Arden theorem. So for that you have to write state equations. Okay, step number one is write state equations. Write state equations. Okay, so how exactly we will write state equations? See, this is the initial state now. So we will write it as like this: q naught is equal to q naught a plus q naught, sorry, q1a, q naught a plus q1a. So what does this mean? See the incoming arrows. Okay, so how we can jump to q naught? We can jump to q naught on if we are at q naught and reading a, or if we are at q1 and reading a. Okay, so q naught a plus q1a, we will reach at q naught. And please try to remember this thing while writing state equations. Initial state will have null also, because without reading anything we are at null at initial state only. Hence we will write here null also. Okay, I hope I have made the point clear. So q naught will be equal to q naught a plus q1a plus null. Okay, now write state equation for q1. For each and every state you have to write it. So q1 state equation of q1 will be what? See the incoming arrows on q1. So we are jumping to q1 with the help of q naught on reading b. So q naught b plus on q1, if we are reading b, then we are at q1 only. So q1 b. Okay, so state equation of q1 will be q naught b plus q1 b. And since we want to convert this FA into regular expression, so we have to solve these two equations for final state only. Okay, so now step number 2 is after writing you can say state equations, step number 2, solve for final states. Solve for final state. But if you have more number of final states, then obviously you have to solve for each of them. Okay, so okay, I will come back. I will come to it later that how will you solve for more than one final state and so on. But just concentrate here, and I'm assuming that we have only one final state, that is q1. Okay, so now step number 2 is solve for final state. So how will you solve for final state? Okay, so this is very simple. See here, can we apply the same Arden theorem? R is equal to q plus rp. Can we apply here? See here carefully. See, let me use a different color. Okay, so R is equal to q. This entire thing is q, and this is R, and this is p. Okay, so this is R, this is p. Okay, and this entire thing is q. So R is equal to q plus rp. So I can apply Arden theorem here itself. This is equation number 1. This is equation number 2. So from 2, okay, from 2, but I can write R is equal to q plus rp, then R is equal to qp star na. So q1 will be equal to q naught b b star, q p star. So p is b na, so b star. So I think you are getting something like regular expression only, but this is not regular expression. Why this is not regular expression? What is this q naught here? What q naught is doing here? Okay, so q naught should not come na. Please see it carefully. bb star is regular expression. What is q naught? Q naught should not come in regular expression. We haven't say a state can come in regular expression also. So now you just have to put the value of q naught and again try to solve it. Okay, so the only problem is q naught here. So try to solve for q naught. Okay, so just see, can we apply Arden theorem on equation number 1? See it carefully. Okay, let me use a different color. See here, R is equal to q. So this entire part will be q, and this will be R, and this will be p. So again, R is equal to Q plus RP. We can do it. So let me do it carefully. So from 1, so we will get R is equal to Q plus RP. So R is equal to QP star now. So R will be equal to QP star. So QP star means what? Q1A plus null. This will be Q P star. So P is A na. So A star. So Q naught will be this thing. Now you just put this value of Q naught in this equation. So let me label this equation as 3 and this equation as 4. So from 3 and 4. Okay. From 3 and 4. Let me use a different color. From 3 and 4. Okay. So you have to put the value of Q naught in this equation 3. Okay, so what will you get? Q1 will be equal to, put the value of Q naught, Q1A plus null A star. I have put the value of Q naught here, then B star. Now tell me, is it regular expression? Obviously, no, this is not a regular expression, because what this Q1 is doing here. Okay, so everything is fit and fine, but what about Q1? Now, as soon as I see Q1 and here also Q1, I will think about of applying your Arden theorem, and I have already shown you that if we have equation like R is equal to Q plus RP, then the equation will be independent of R. Sorry, the solution will be independent of R. Huh? R is equal to Q plus RP, solution was independent of R. That means you will get QP star only. So see here. Let me jump to the next slide. See here carefully. Okay, so please note it down. Okay, yeah. So see here, R is equal to, okay, so again I will not be able to apply it directly, but just I am trying to show you. R is equal to, say, this will be R na. So first let us open it, then you will get the proper idea. I am just showing you that here also Q1, here also Q1. Then obviously we can think of applying Arden theorem, and we can get rid of Q1 very easily from here. Okay, so let me show you proper idea. Okay, so how we are going to do, let me show you properly. See, so now we just open it. So Q1 will become Q1 A, then you just concat A star. I am just opening the bracket, BB star plus null dot something is something only, so A star BB star. Now apply Arden theorem. Okay, you will get the proper idea. Now just try to apply the Arden theorem. Okay, so see here, what is this? R is equal to Q plus R, and this entire thing is P. R is equal to Q plus RP. So just solve it. You will get your answer. So Q1 will be equal to, R is equal to QP star na. So A star B star P star. So P is this thing, entire this thing. A star B star whole star. This is your final answer. So this is your regular expression for the state Q1. Okay, so if Q1 is final, then you will get this as your regular expression. Now just try to see here. If Q0 is also final, then no problem. Similar idea you will use and solve for Q0, and you will just add plus in between them. Okay, so you will just OR them, or you will just union them. So if this is the regular expression, so let me show you properly. So if R1 regular expression came for Q1 and R2 regular expression came for Q2, and if both are final, Q1 is also final and Q2 is also final, then you will just write R1 plus R2. This is your final regular expression for FA. Okay, I hope I have made the point clear to all of you. So if even 3 final state, then solve for all the solve for Q1, Q2, Q3 and apply plus between them. That's it. Okay. So I hope I have made the point clear. Now one more point I want to specify here. There is another method also for you can say solving these equations. So I see here. First, I have applied the Arden theorem. Na? On 2 itself, I have applied the Arden theorem and I have solved it and so on. I can directly put the value of Q0 here also. Then you will get the difference answer. Okay, so the only thing is we have 2 equations and 2 unknowns. What are the 2 unknowns? Q0 and Q1. It's entirely depends on you how exactly you solve it, and you may get a different answer also. And by the way, I should tell you that this is a question of UGC-Net. Okay, this question came in UGC-Net exam. See, whatever question I am solving in these lectures, these are either from GATE, NET, or other competitive exams. Okay, so don't worry, I'm not picking questions randomly. I'm picking questions from all these exams only. Okay, so this question came in UGC-Net. I think in 2012 itself it came. Okay, so I just want to confirm, or I just want to say you that uh, we have two equations and two unknowns. It entirely depends on you how you solve these unknowns. Okay, so there are other methods also. Okay, so let me show you one more method. Okay, it's coming in my mind, so let me show you another method also. I have solved it for what? See, I have applied Arden theorem directly on Q1. Okay, and then we get answer in the form of Q naught. Na, see, I have directly applied Arden theorem and I have got answer in the form of Q naught. Then I solve for I solve Q naught and I get the answer in terms of Q1, and then put the value and get the answer. Another way can be directly put value of Q naught in this equation. Okay, so see what exactly we get here. Okay, I can of course give you this thing in homework also, but let me give you idea about what I'm going to say here. Okay, so see, Q naught is this Q naught A plus Q1 A plus null. Okay, so apply Arden theorem on Q naught, you will get this thing, and you just put this thing, okay, this the value of Q naught in this equation itself, and then apply Arden theorem, you will get a different answer. Okay, so let me show you what exactly I am saying. See, you just solve for Q naught. So I have already solved for Q naught. Now I have got this answer. Now I will put this thing in two equation. Okay, so from 4 and 2, let me show it here. From 4 and 2, what will we get? So I will get Q1 will be equal to, put the value of Q naught, that is Q1 A plus null A star. Okay, so I have put the value of Q naught, then after that I have B plus Q1 B. This is a new equation which I am getting. Now what I will do, I will try to open it up. So Q1 will be equal to Q1 A star B plus A star B plus Q1 B. Now I will take Q1 as common and see what I'm going to get. A star B plus B plus A star B. So Q1 will be this. I hope I have made the point here. Just I have taken Q1 common. Okay, from this and this. From this and from this, I have taken Q1 common and I have got this thing. Why I have taken common? So that I get proper P star. Na? So see, now this is in the form of Arden theorem. R is equal to Q plus R T. R will be equal to QP star. So Q1 will be equal to A star B, then A star B plus B whole star. This is again a new type of regular expression which I am getting. And since I have just followed the Arden theorem only, but I have just twisted the answer. Okay, so please try to note it down that these two regular expressions are exactly same, exactly equivalent. Exactly equivalent means just try to put I can say that if any string is present in this regular expression, then that will be present here also, and vice versa. Okay, so if you want to check, then I can show you easily. See here, let me put everything on one slide so that you can get it properly. Okay, so see here what we are doing. A star B, see here, A star B. Okay, after reading A star B, we are at Q1. Okay, so now A star B, so again A star B plus B, na? So plus B also, and whole star, so you can get everything. See, I have just given you hint that why this regular expression is correct. If you are able to follow, then it's okay. Then otherwise you can leave it. I'm just trying to explain it again. See, A star B, you will be at Q1. That is your final state. Now see here, A star B. See the loop. A star B, A star B, or you can say B also, because B self loop also on Q1. A star B or B. That means what? Plus. So A star B plus B, and you can take it any number of times. So hence I have applied star here. Okay. Similarly, you can prove this expression is also correct. See here, A star B B star, A star B B star. You are at final. Now what you are saying is A star B B star whole star, because you can take any number of times. See, A star B B star, then again A star B B star, A star B B star, and so on. Okay, so if you are able to follow, then it's really nice. Otherwise, please rewind the video and watch it again. I'm not going to explain it again and again. It's just wastage of time. Okay, so please note it down, each and everything very carefully. I have put everything on one slide so that you can note it down. This is all about Arden theorem. Of course, I have solved only one question. I want to solve other questions also, but it will take a lot of time, and I have just given you ideas. Since this is a basic course, so I am keeping the things very basic only. Okay, I'm not going into pretty much detail and so on, but I have just given you idea, and I hope if you have got this properly, then you can solve any question on Arden theorem very easily. Okay, either if FA has 3 state, 4 state, and so on, you can solve it easily. Yeah, so just give me one idea that if we have 4 state, then obviously we will have 4 equations and 4 unknown. If you are able to solve 2 equation, 2 unknown, then obviously you will be able to solve 3 equation, 3 unknown, 4 equation, 4 unknown, 5 equation, 5 unknown, and so on. Of course, that will be that will become a bit bulky, and it will take, or it will consume a lot of time, but no problem, we can easily solve it. Okay, so please note it down. Now I'm jumping to next slide. So we are now at the last topic of your chapter 2, that is finite automata and regular language, that is 13th topic, pumping lemma. Okay, so just first I will build a basic concept, or you can say basic idea, okay, or basic background. Then I will jump to pumping lemma properly. So question I'm saying is, if FA has n states, then maximum length of string accepted by it without loop will be. Very simple question. See, let me give you some idea. Q0. On reading A, we are going to Q1. On reading B, we are going to Q2. On reading A, we are going to Q3. Okay, and on reading C, we are going to Q4. Q4 is my final state. So what is the maximum length of string? See, number of states here are what? State number 1, state number 2, state number 3, state number 4, state number 5. We have 5 states. So maximum length of string which is accepted by this FA without loop. See here what I am using the word maximum length. I am not concentrating on minimum length. I am concentrating on maximum length. Minimum length can be 0 also. If initial is final, then null string will be accepted. Null string accepted means what? Length is 0. Okay, so I am not concentrating on minimum length. I am concentrating on maximum length. So we have 5 state. Maximum length of string is what? A, B, A, C. So maximum length of string is A, B, A, C. Okay, A, B, A, C. That means what? If we have 5 states, then maximum length of string accepted by this FA without loop will be of 4 length only. Okay, that means what? If we have string of length 5 or more, which is accepted by this FA, then there exists at least one loop, or you can say at least one loop is accessed. Loop means what? State is repeated. Like, see here, if I have a self loop of say D here, so if my string accepted is A, B, D, A, C, that means what? I have repeated state Q2 2 times. That means what? On Q1, after reading B, we are at Q2. Then on reading D also, we are at Q2 only. So Q2 is accessed twice. That means what? Loop has been accessed. So if we have a string of length 5 or more, see, this string length is 5, and this string length 5 is accepted by this FA, and states are also 5. That means what? There exists at least one state which is repeated. Okay, so that means what? If we have I can generalize it. If FA has n state, then maximum length of string accepted by it without loop will be n minus 1. Okay, so maximum length of string accepted by it will be n minus 1. So n minus 1 is my answer. So indirectly, I can also say that if FA is accepting string of length greater than or equal to n, that means what? There exists at least one loop. That means at least one loop is accessed, or you can say you have accessed any state at least 2 times. So proof of this statement is very simple. You can get it with the help of Pigeonhole Principle. I hope you know about what exactly is Pigeonhole Principle. I'm not going it in details of these principle and so on, but let me give you just idea. Okay, so if you have m pigeons and n pigeonholes, okay, so if you have m pigeons and n pigeonholes, see, these are n pigeonholes. Okay, so, or let me say it simply, 4 pigeonholes and pigeons are 5. pigeons are 5. So what will you do? So I will say, of course, that if you put one pigeon in each, you can say pigeon 1 here, pigeon 2 here, pigeon 3 here, pigeon 4 here. So in worst case, you can do what? You can keep each and try to put each and every pigeon in different hole. But what about my fifth pigeon? Fifth pigeon will be kept either here, 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 or here. That means what? This is guaranteed that at least one pigeonhole will have 2 or more pigeons. Okay, so directly, indirectly, I'm saying is if we have m pigeons and n pigeonholes and m is greater than n, that means what? Number of pigeons are more than pigeonholes, then obviously at least one pigeonhole will have 2 or more pigeons. Okay, so this is the very simple principle, but it has lots and lots of applications. Okay, we will study them in discrete mathematics. So pigeonhole principle, you can say we have applied. Okay, so with the help of pigeonhole principle, we can prove that if length of string is greater than or equal to n and number of states in FA is also n, then obviously there exists a loop. There exists loop means what? There at least one state will be repeated. Of course, you can apply pigeonhole principle and just do common sense and you will get your answer. Okay, so I need not explain each and everything, but I think you are getting the intuition behind pumping lemma. So the proof of pumping lemma is with the help of pigeonhole principle only. Of course, I have not told you about what exactly is pigeonhole principle. I am just you can say giving you idea, or I'm just making background for pumping lemma. But I hope you are getting few idea. You are getting something from it. Okay, so from pigeonhole principle, I can give the statement that if number of states in FA is if the length of string accepted by FA is greater than or equal to n, then there exists at least one loop. Okay, so this statement is from pigeonhole principle. Okay, now question number 2 is, see question number 2, what is the maximum and minimum content of loop if string accepted is of length n and number of states in FA is also n? Length of string is n and number of states in FA is also n. So I have told you in the previous slide itself that if length is greater than n minus 1, or you can say greater than or equal to n. See, these are one and the same thing, greater than n minus 1 or greater than or equal to n or greater than or equal to n. These are one and the same thing now. So if I say, if I'm saying I'm already given you that length of string is n, that means what? There is just at least one loop. So at least one loop should be accessed, or you can say at least one state should be repeated. So now I'm considering on content of loop. What should be the content of loop? So let me give you some idea. You will get the answer. Q0. On reading A, we are going to Q1. On reading B, we are remaining on Q1. On reading C, we are going to Q2. Q2 is our final state. So let me take a string as ABC. W string is ABC. So see the length of string is 3 and number of states in FA is also 3. So this is according to condition given in the question. And I will directly say by pigeonhole principle at least one state should be repeated. And this Q1 is obviously repeated. You can guess it also. After reading A, we are at Q1. From starting from initial state, after reading A, we are at Q1, and on reading B, we are again at Q1. So Q1 state is repeated 2 times. Okay. So there exists a loop. Now, what is the content of loop? Content of loop is B only. Okay, so content of loop is B. Okay, so minimum content of loop should be 1. You cannot say minimum content of loop is 0. If content of loop is 0, that means what? You have not accessed the loop. If you have not accessed the loop, then how length of string is n? Okay, so minimum content of loop will be 1. Minimum content will be 1. What about the maximum content? Maximum content is also very easy. See this FA, Q0. On reading A, we are going to Q1. On reading B, we are going to Q2. And on reading C, we are at Q0. Okay, so see here, string W accepted is ABC. Now this ABC, entire this ABC is in the loop now. So what can I say? Maximum content can be entire string itself, that is maximum content can be n. Okay, so if length of string is n and FA has also n states, then maximum content will be n itself. And this n is what? Please try to remember, this n is the number of states in FA. Okay, so if FA has 5 states, then maximum content of loop can be 5. If FA has 10 states, then maximum content of loop can be 10. If FA has 500 states, then maximum content of loop can be 500, and so on. How we are getting it is in this format only. Okay, So I hope I have made the point clear to all of you. Okay, so let me do it properly also. So this is your final also. Okay, so string accepted now, we have said that string accepted is of length n. So so abc string must be accepted now, so initial should be the final. So w abc. Okay, I hope I have made the point clear. So here in the first case, the minimum content was only that, means the self loop we are getting, or you can say yeah. So here minimum content is 1 and the maximum content is here, that is a number of states itself. So minimum content 1, maximum content n. Okay, so summary I can say it, minimum content, so a content of loop, if I say content of loop, then will what will you say? Content of loop will be from 1 to n. N is what? Number of states in FA. Number of states in FA. Okay, so I hope I have made the point clear. Please note it down. These all things are, you can say, background of your pumping lemma. Okay, so if you have got these two questions, then obviously you will get pumping lemma very easily. See now, pumping lemma for regular languages. So see, we are doing it for regular languages. We have also for CFL also pumping lemma for contextual languages also, but it's not in the syllabus, so we will not concentrate on that thing. Okay, so pumping lemma for regular languages, I have written 3 notes, so please try to follow them properly. The first note is pumping lemma gives necessary condition but not sufficient condition for language to be regular. This is very, very important point, and please note it down carefully. And this question came in various competitive exams like GATE, NET, etc. in different format. So what exactly this is saying? Necessary condition means, if see, pumping lemma necessary condition. Let me show you properly. If pumping lemma is necessary condition, I'm writing it in short format to save the time only. Pumping lemma is necessary condition. That means what? If pumping lemma fails, we can say that language is not regular. But if pumping lemma test pass, this is a test, okay? So if pumping lemma test pass, then it may or may not be regular. Okay, now if in the question itself they can say that what if pumping lemma is sufficient condition, then what will you say? If pumping lemma fails, then language may or may not be regular, but pumping lemma pass, then language will be regular. Okay, so please try to note it down carefully. I'm just trying to explain that what exactly is necessary condition, what exactly is sufficient condition. Necessary condition means if necessary condition fails, then hypothesis fails. But if necessary condition passes, then we cannot say about hypothesis may be true or false. Necessary means what? This is the basic necessity. If basic necessity is not even fulfilled, then obviously you will say that my hypothesis is false. But if your basic necessity is fulfilled, then hypothesis may be true or false. I cannot say anything. So what about sufficient condition? Sufficient condition means this is sufficient for me. Sufficient means what? If this condition passes, then hypothesis also passes, or you can say hypothesis is correct because this is sufficient. But if sufficient condition fails, then hypothesis may pass or may fail. We cannot say anything. That means no comment. Okay, so last time I am repeating, necessary condition fails, then hypothesis fails. Necessary condition. So pumping lemma necessary condition means if pumping lemma fails, then language is not regular. If pumping lemma passes, then language may or may not be regular. Sufficient condition means if pumping lemma fails, then it may or may not be regular. But if pumping lemma passes, then language should be regular. So pumping lemma is not a sufficient condition. It is only a necessary condition. That means what? If pumping lemma test fails, then language is not regular. But if pumping lemma test passes, then language may or may not be regular. So what do you think? What exactly we are doing with the help of pumping lemma? We are trying to prove with the help of pumping lemma, we are trying to prove language is not regular. Okay, so let me write it properly so that you get the idea. So we are going with the help of pumping lemma, we are going to prove L is not regular. We are not going to prove that language is regular. Please note it down carefully. The same question came, I think, at least 10 times in GATE as well as NET exam. In various competitive exams, same question came again and again by changing the language of the question. So with the help of pumping lemma, we are going to prove L is not regular. We cannot prove with the help of pumping lemma that language is regular. Okay, pumping lemma can't prove. Pumping lemma can't prove L is regular. It cannot prove L is regular. It can prove only L is not regular. That means what? It is a negative test. It is not a positive test. Okay, so it can be used with negative way only. It cannot be used for positive ways. Okay, I hope I have made the point clear. So this is the first important point which you should remember. Pumping lemma give necessary condition but not sufficient condition for language to be regular. Next is pumping lemma is based on Pigeonhole principle. I have already told you, or I have already given you idea about what exactly is Pigeonhole principle and so on. So it is based on Pigeonhole principle, and pumping lemma uses proof by contradiction. What is proof by contradiction? It means that we will assume that language is regular, and finally we will arrive at contradiction, and hence we will show that language is not regular. Okay, so proof by contradiction means we will assume language is regular, assume L is regular, and then finally by following some steps we will arrive at contradiction. This is the symbol of contradiction. Okay, like this arrow pointing each other. This is a contradiction. So after following few steps we will come at contradiction, and hence we will say that our assumption was wrong, that is L is not regular. Like this we will prove. Don't worry, I will jump to prove, then you will get the idea. Okay, so just try to note it down everything. Okay, I will put everything on one slide so that you can note it down properly. Okay, so note it down, please note it down. Okay, now next. So now we will try to solve this question, how to prove L is not regular with using pumping lemma. So how will you prove? See here carefully, how to prove L is not regular with the help of pumping lemma. So step number one, as I have already told you, proof by contradiction. Now, so we will assume that L is regular. Now, since L is regular, so what does this mean? There is this FA of n states accepting L. Obviously, now if L is regular, then there is this FA of n states. Let us we do not know about n. Really, we do not know about n. What exactly n is? I'm just saying that there should be FA of n states which is accepting L. Okay. Now, assume a string W. Next step is assume a string W which belong to L, and length of W should be greater than or equal to n. We will take a W which is in the language, and length of W is greater than or equal to n. What does this mean? I have already told you, if string length is greater than or equal to n, then there is in acceptance path there is at least one loop. I have already told you. Please see the previous slide. I have already told you. Pumping out length n, number of states is also n, content of loop. Na? This, first question C. If FA is n state, then maximum length of string accepted by it without loop will be n minus 1. So if string length is n or greater than or equal to string length is greater than or equal to n, then there is at least one loop. Proof was with the help of Pigeonhole principle. I have already told you. This was the question number 1 itself. That's why I was saying again and again that this is the basic background of pumping lemma. These two questions are background. Okay, so let me come here. So I have already told that assume a string W belong to L, length of W is greater than or equal to n. So in an acceptance path there exists at least one loop. So how I'm getting step number 4? Proof of step number 4 is by Pigeonhole principle. Okay. Next step is divide W into 3 parts. You will divide W into 3 parts. That is X, Y, Z. X is what? X is what? X is content of W. Okay, content of W before start of first loop. Before start of first loop, that is the X. Y is content of first loop. Z is the remaining part of W. Okay, so let me give you some example, then you will get this idea properly, or let me use the idea of the previous slide itself. You will get the answer here. Okay, so see here. Okay, so let me build it properly, otherwise you will get confused. Okay, so you have to jump on different slides. So let me do it properly here itself. Okay, so it will take hardly 1 or 2 minutes, but you will get the proper idea. So Q0, this is your initial state. On reading A, we are jumping to Q1. On reading B, we are jumping to Q1 only. On reading C, we are jumping to Q2. Q2 is our final state. If we take W as A, B, C, see here, string of length 3 and number of states are also 3. So length of W is greater than or equal to 3 now. So I can take this string W and divide this string into 3 parts. Please see it carefully. If I take W as AC, AC is also accepted AC is also accepted by this FA, but I cannot take it as W for our pumping lemma, because for pumping lemma number of states in FA is 3. So we should take string of length 3 greater than or equal to 3, so that in acceptance path there exists at least one loop. But here string of length 2 and there is no loop at all. So we cannot take this as W for our pumping lemma, but we can take this string as W for our pumping lemma. And what will be my X, Y, and Z? Content of W before start of first loop. So see, there can be, we have designed only one loop here, but we can have multiple loops also. I'm not going into that much detail, but I'm saying that we have used the word na there exists loop. So we can have more than one loop also. So if we have more than one loop, then you have to concentrate on the first loop itself. So first loop, before start of first loop, what is the content of W? So content of W is A only before start of first loop. Now content of first loop, that is B, and remaining part of W, that is C. This is the X, Y, Z. If you take W as A triple B C, what is X, Y, Z? Please try to explain me. Okay, so content of W before start of first loop. Before start of first loop, content of W, that is A. Content of first loop, C, content of first loop, that is B only. Content of loop. Okay, now remaining part of W, that will be C. So double BC will be Z. I hope I have made the point clear to all of you. So this is all about X, Y, Z. Okay, now if W belong to L, then all W dash will also belong to L. How will you prove? If W belong to L, for then all W dash belong to L, where W dash is what? Where W dash is what? Okay, so let me first tell you about W dash, then we will prove. Okay, so if W belong to L, then all W dash belong to L, where W dash is what? Here W dash is X, Y power I, Z, where I is greater than or equal to 0. Okay, where I is greater than or equal to 0. So if I put I is equal to 0, then XZ should be accepted. See here W, A, B, C. Okay, so we have divided into three parts now, X, Y, and Z. So if I'm saying that W belongs to, if W belongs to L, then all W dash will also belong to L, X, Y power I, Z. I is greater than or equal to 0. See here, proof of this statement. See here, I will verify this statement here. See, W belong to L, ABC is accepted. Now I am saying that all W dash will also belong to L, where W dash is X, Y power I, Z. So see, put I is equal to 0, then we should get XZ. XZ means here what? AC. So AC should be accepted. Yes, AC is accepted. Okay, if I take I is equal to 0, then we will get AC is accepted. I is equal to 1, then ABC is also accepted. I is equal to 2 means what? X, Y, Y, Z. Now Y is what? B na. So A X, Y power 2Z Y power 2Z na. See, we will get X, Y power 2Z when I is equal to 2. That is what? X, Y, Y, Z. Y is what? B here. So we will get A, B, B, C. A, B, B, C is also accepted. Similarly, if I put I is equal to 3, then we will get A triple B, C. That is also accepted, and so on. So now I am using the technical word. I can pump this B any number of times and still string will be accepted. Hence, the name is pumping lemma. So why we are using the word pumping lemma? Because we can pump this B any number of times and still string will be accepted. Okay, I hope I have made the point clear. So here, see, I have verified this step 6. Now I have already told that if W belong to L, then all W dash will also belong to L. But we will try to find a W dash. If W belong to L, then all W dash will also belong to L. Now we will try to find a W dash which does not belong to L. If I get success in finding a W dash which does not belong to L, then obviously we will come at contradiction, because we have already told in step number 6 that if W belong to L, then all W dash will belong to L. And I have find a W dash which does not belong to L. That means what? This is a contradiction. Hence, we will say that language is not regular. Okay, I hope I have made the point clear. Now, what can you say about this thing? Obviously, pumping lemma test passes here, but I will not say that language is regular, because pumping lemma passes means what? This is necessary condition. It is not a sufficient condition. If pumping lemma test passes, then language may or may not be regular. But if pumping lemma test fail, then language will not be regular. So with the help of pumping lemma, we can prove that language is not regular. We cannot prove that language is regular with the help of pumping lemma. Okay, we can only prove that language is not regular with the help of pumping lemma. I hope I have made the point clear, and I have repeated it again and again so that you get the clarity of the concept. Okay, so please note it down carefully. Let me put everything on one slide so that you can note it down carefully. Okay, and then we will try to prove. We will take some language, or we will take some non-regular language, and we will try to prove that it is not regular with the help of pumping lemma. Please note it down carefully. Okay. Now I'm jumping to next slide. I hope you have noted down carefully. Okay. Yeah. So see, prove that L is a power n square, n is greater than or equal to 0, is not regular. With the help of pumping lemma, we are going to prove it. Okay. So how we will prove it? See, same steps. Okay. So step number 1 will be what? Assume L is regular. I am writing in the short manner to save the time. Let L is regular. Since L is regular, so there exists FA. There exists FA of n states accepting L. There should be some FA, na? FA, there exists FA of n states accepting L. Now, step number 3. Since we have a FA, so see the previous slide so that I can copy paste everything and I can save the time also. Okay, so I'm jumping to previous slide just to save the time. So there is FA of n state. Now, as assume a string W belong to L and length of W is greater than or equal to n. Okay, so I'm writing here just to save the time. S3 will be what? Step number 3 will be there exists W belong to L, or take W belong to L. Okay, so let me write it properly. Take W belong to L and length of W is greater than or equal to n. Step number 4, there exists loop. Okay, if length of W is greater than or equal to n, so there exists a loop. Step number 5, we will divide W into 3 parts, that is X, Y, and Z. Okay, yeah, and actually I forgot one thing. So let me jump to the slide so that I can show you in pumping lemma. Actually, I have told you everything, but still I'm concentrating, or you can say I'm telling you again and again so that you get the proper clarity. What should be the minimum length and maximum length of Y? Okay, so Y length minimum should be 1 and maximum should be n. This can be easily proven. Why Y should be minimum 1? Because if Y is 0, or you can say content of first loop is 0, that means what we have not accessed the loop. If we have not accessed the loop, then how I am taking W whose length is greater than or equal to 1? Okay, so W should not be greater than or equal to n. W should be less than or equal to n minus. I have already told you in the I have discussed 2 questions now. In that two questions, I have already told you. See the slides. See the slides properly. See, without loop means what? Length should be n minus 1. If length is greater than or equal to n, then there should be a loop. Now I am taking a W. I am taking a W whose length is greater than or equal to n. See here properly. Assume a string W whose length is greater than or equal to n. So there should be a loop. There should be a loop means what? Minimum content should be 1. See the question number 2. You will get more clarity. Minimum content of loop was what? 1, and maximum was what? N. So same I am writing here. So minimum content of loop should be 1. It cannot be 0. If it is 0, that means loop has not been accessed. If loop has not been accessed, then how length of W is greater than or equal to N? Okay, so it should be greater than or equal to 1. Why maximum N? I have already told you in the question number 2. Then it cannot exceed N. If we have N states in FA, then obviously content of loop can be entire. It will cover each and every state exactly once. Na? So this entire thing should can become a loop. Na? See, like here, Q0, A Q1, B Q2, and like C here. Okay, so these symbols need not be same. These need not be different. I'm using ABC, so you can put here A, B, A, or you can put here A also. Okay, and this is my final state. So maximum content of loop is what? Triple A, and number of states are also 3. Okay, so it depends on FA only. Everything is common sense. If you, the more you think, the more you get. This is the basic rule of TOC, of studying TOC. The more you think, the more you get. Okay, so maximum content of loop can be n, where what is n? N is the number of states. There is a FA of n states now, so n is the number of states. Okay, now let's jump to our slide. You have got the idea, so let me jump here. Okay, so step number 5 will be, we will divide W into 3 parts, that is X, Y, Z. Okay, so x is what content of w before start of first loop, y is what content of loop, and z is what content of w after first loop. Okay, so we have divided w into three parts, that is x, y, z. Now what I will say, see, w, length of w. Okay, so length of w, I'm taking from, just for the sake of simplicity, I'm taking, see, I can take any w whose length is greater than or equal to n. So I am taking, so let length of w is equal to n square. Okay, so if FA has n states, then I am taking length of w as n square. So if FA has 5 states, then I am taking w of length 25. If FA has 4 states, then I am taking w of length 16. If FA has 3 states, then I am taking length of w as 9, and so on. So this is just for the sake of convenience, so that I can prove easily that why it is not regular. So I am taking length of w as n square. Okay, so length of w I am taking as n square. Okay, now I will say step number 6. Step number 6 is what? If w belong to L, then all w dash, okay, all w dash should belong to L, where w dash is what? W dash is x, y power I, z, such that I is greater than equal to 0. Okay, this is your step number 6. Now I just need to find step number 7 is what? Find a w dash. Find a w dash which does not belong to L. If I am able to find a w dash which does not belong to L, then I will say I have arrived at contradiction, and hence our assumption was wrong. That means L should not be regular. Okay, so now just try to find a w dash. How will you find a w dash? So for finding a w dash which does not belong to L, we have to assume value of I. Okay, let me use a different color. We have to assume a value of I. So let us take, for our convenience, let us take I is equal to 2 here. Again, you may be thinking that why I am taking length of w as n square and why I am taking as I is equal to 2. It's just for the sake of convenience, so that I can prove it properly. Okay, and it is a basic course, and in basic course itself, I am telling you advanced questions, and I am properly telling you, or I am showing you, you can say formally or mathematically, how you can prove a language to be non-regular with the help of pumping lemma. I should not have explained such type of questions, but I am explaining it so that you get the proper idea about how exactly pumping lemma can be used to prove language is not regular with the language is not regular. Okay, so how we can prove? So that's why I am explaining it in a bit formal way. So you just have to remember that, I'm, for, you can say, for convenience, or you can say for simplicity, I am taking length of w as n square, and I am taking, we need to find a w dash which does not belong to n. So for finding that w dash, I am taking I is equal to 2 here. So what will be my w dash now? Since I am taking I is equal to 2, so w dash will be what? X, y power 2z. So that will be what? X, y, y, z. Okay, so now w dash is this thing. Now length of w dash will be what? Length of w dash will be what? X, y, y, z. Length of x, y, y, z. Length of x, y, y, z. Now, according to my experience, when I used to teach, I have experience of around 12 years. So I have taught in various institutes and various universities also. And according to my experience, many students feel difficulty in this step. So please try to concentrate here. X, y, y, z. Now, length of x, y, y, z, I can put it like this also. Length of x, y, z part plus length of y. You should not get confused in this step, because this is very basic thing. We are finding the length. So x, y, y, z, length of x, y, y, z will be what? Length of x, y, y, z will be what? Length of x plus length of y plus length of y plus length of z. Now x, length of x plus length of y plus length of z, that will be what? Length of x, y, z plus length of y. So I have explained it properly. Please try to follow it. If you are not able to follow, please rewind the video and watch it again. This is a recorded session, so you should be able to watch it again and again. Please watch it again and again till you are not able to get it. Okay, now x, y, z plus length of y. Length of x, y, z is what? N square. I have already told you I am taking a w whose length is n square. Now you will get the idea of why I have used length of W as n square. Okay, and why I have used I is equal to 2, you will get now properly. So XYZ length is n square. What about my length of Y? Length of Y, minimum length will be 1 and maximum length can be n. I have already told you a few minutes back, I have already told you that length of Y should be minimum 1 and maximum n. Okay, so what can I say? Length of W dash. What can I say about length of W dash? Please see here carefully. Length of W dash should be greater than or equal to n square plus 1, because length of Y minimum 1. Length of Y should be minimum 1. So it should be greater than or equal to n square plus 1, and it should be less than or equal to n square plus n. Have you got it properly? Please see it carefully. XYZ length is n square. Length of Y should be minimum 1 and maximum n. So minimum 1 na. So length of W dash should be any number between n square plus 1 and n square plus n. Now let me show you more precisely. So since W dash is greater than or equal to n square plus 1, so W dash should be strictly greater than n square. This is very basic thing. If any number, if x is greater than or equal to 3, then obviously x should be strictly greater than 2. This is the very basic thing. Na? So I have used the same concept. So W dash should be strictly greater than n square. And what about here? N square plus n. Na? So I can keep here n square plus n plus 1 plus n. Okay, or let me do it properly. N square plus n plus 1. See, if some quantity is already shorter, n is say less than equal to 5, then obviously n is less than equal to 1000 also. What a big deal. I can keep it n can be less than equal to 100 also, n should be less than equal to 1000 also, and so on. If n is less than 5, I am assuming something. If n is less than equal to 5, then n should be obviously less than equal to 100, less than equal to 1000, and so on. So same idea here also. Or let me do it properly. Okay, so let me put like this. Okay, let us remove that equal symbol, because if n is less than equal to 5, then I can also say that n should be strictly less than 100. It should be strictly less than 1000. Similar idea. Okay, n is less than equal to 5, then obviously n is strictly less than 100. It is strictly less than 1000 and so on. So similar idea I have used here. So W dash should be strictly less than n square plus n plus 1. Why I have used this n plus 1? You will get the idea. Please have patience. So W dash length will be what? N square, and this is what? N plus 1 whole square. So length of W dash is lying exactly between two consecutive squares. This is a contradiction, because I have said already a power n square. So what about this language? So smallest possible string will be null when n is equal to 0. Then a power 1, then a power, when n will be 2, then a power 4 will we get. When n is 3, a power 9, then a power 16, then a power 25, a power 36, and so on. That means all are perfect squares. Length should be perfect square. But I am getting length of W dash. I am getting length of W dash as exactly between two consecutive perfect squares. Okay, so this is a contradiction, and I have succeeded in finding a W dash which does not belong to L. Hence, we are at contradiction. So we will say that we have assumed that L is regular. This assumption is wrong, and L is not regular. That means pumping lemma test fails here. Okay, so please try to copy it properly and just try to understand what exactly I have said and what exactly I have used in this session. Okay, so just try to focus here and try to concentrate and try to note down each and everything properly. And I hope you are getting everything on one slide and you are able to note it down properly. Or you can say note it down in parts. First note down the question and this example. Okay, and now see, you have got everything in one slide. Please note it down carefully. Okay, so this is all about pumping lemma, and this was the formal proof. Intuitive proof, we can use intuitive proof also. Okay, let me give you one idea of intuitive proof. Okay, so see here, I have already told you that if we have comparison between A and B, then language is not regular. I have already told you. Now I'm going to prove it with the help of pumping lemma that A power and B power n is not regular. I will say very easily. See, assume that language is regular. Now, if language is regular, step number 1 is what? Assume language regular. If it is regular, then there exists FA. Step number 2 means what? There exists FA. of n states. Step number 3. Okay, or leave all these things. I'm not going to prove it formally. I'm just giving you idea. Assume that it is regular. If this is regular, then it is FA. Now, if FA has n state, then take a W as a power m b power m, such that m is greater than or equal to n. Directly and indirectly, what I'm going to say is, if you have taken m greater than or equal to n, so in acceptance path of a power m b power m, we will have a loop, and that loop will be of a's only. Now, since that loop will be of a's, so we can pump a any number of times. Since we can pump any number of times a's, then how will we will control b's? Okay, so this is the intuitive idea. How will you control b's? So we cannot have control over b's. That means we cannot say that, we cannot guarantee that a's and b should be equal. I'm see, intuitive idea is like this: q naught. On reading a, we are jumping to q1. I'm just giving you idea. q2. On a, we are jumping to say q3. Now on q3 we have a loop of a, or you can say we have a loop like this, or you can say we have a loop like this, or we have a loop like this. Now after that we are reading b and we are jumping somewhere and so on. Since we have a loop here that is of a's only, so on q3 we can pump any number of a's. Or if we if you forget about this, okay, if you forget about this, then leave it. We have a loop like this. Let me do it step by step so that you get proper clarity. Okay, so leave all this. Okay, if you have a loop like this, so I can say on jumping to on whenever we are q2, after reading a we are jumping to q3, and after reading a we are jumping to q2. So we can pump a's any number of times. How will you prove that a's and b's are equal? So this is, you can say, number of a's and b's may or may not be equal. So language is not regular, or you can say this is not the FA. Okay, this is not the FA. Now if we have a loop here, of course this is not the FA again, because we can pump a any number of times. So how will you control the number of a's and number of b's are equal? Okay, and if you have like this, again we can pump a any number of times in this loop. So how will you guarantee that number of a's and b's are equal? So I hope I have made the point clear that a power and b power n is not regular, because we cannot keep a count on a's and b's. Okay, so if we have a loop, then in that loop we can pump a's any number of times, then we cannot keep a count on b's. Okay, I hope I have made the point clear to all of you. Hence a power and b power n is not regular. With the help of pumping lemma we have proved it. Of course we have not proved it formally, but I have given you intuitive idea. Intuition is the main thing. Okay, to clear any competitive exam, intuition is the main thing. Okay, that's it. Best of luck to all of you. This is our first second chapter is already completed. Now we will jump to the third chapter, that is PDA and CFLs and PDAs. This chapter is not too much long. This the first chapter I have already told you that more than 50% of TOC syllabus will be completed in the second chapter itself. Sorry, it is not first chapter, it is second chapter. So more than 50% of syllabus is completed in the third and fourth chapter. These are very small chapters. So in the next class itself we will start your third chapter, that is CFLs and PDAs, and I hope I will try to complete it in 4 to 5 lectures, and the last 5 lectures will be dedicated to your chapter 4 of TOC, that is Turing machines and decidability. Okay, thank you so much. Bye bye.